Hi, my name is Yuchi Tai. Today, I'm going to present a high-resolution panel for uncovering repeat expansions that cause ataxias. For disclosure, I am an employee at Pacific Biosciences. In this study, we used the No-Amp targeted sequencing method to target and sequence 17 different repeat expansion loci in human genome. There is 15 different spinal cerebellar ataxias and Huntington's disease and Fragile X associated ataxia in the panel. The No-Amp targeted sequencing method uses CRISPR-Cas9 nuclease with a pair of guide RNAs to excise each target region for sequencing. The method does not rely on any PCR amplifications. The sequencing library prep begins with dephosphorylate genomic DNA to block unwanted sequencing adapter ligation, followed by CRISPR-Cas9 digestion to cut out the target fragments. In the next step, sequencing adapter is ligated with the target fragments to form SMARTbell templates for sequencing. Finally, exonuclease treatment would remove any DNA molecules with exposed 3' and 5' DNA ends. The sequencing data is collected with PacBio sequencing platform. We have selected 13 patient DNA samples for this study with either known or unknown clinical diagnosis. The DNA is extracted from cerebellum tissues using Circulomics nanobind DNA extraction kit. The DNA samples with confirmed diagnosis includes one Friedreich's ataxia sample, one Huntington disease sample, and several different samples with SCA subtypes. I would like to point out the sample number 8, although it was diagnosed as having SCA3, there was conflicting data between clinical diagnosis and the neuropathological diagnosis. There is also 4 unknown clinical samples in this study. After we have collected the sequencing data, we first generate circular consensus HiFi reads and demultiplex the data with unique barcodes. On-target sequencing reads were identified by mapping the data against human reference. The coverage plot on the top of this slide shows a sequencing coverage from one of the sample with sequencing coverage on all 17 target regions. To look for repeat expansion in the sequencing data, we can either generate this what we call waterfall plots, so we can visually look at the data to identify sequence interruptions and also repeat expansions. But in order to make the process easier to identify repeat expansions, we used a k-means clustering algorithm to cluster the sequencing reads into 2 repeat length beams. So in this slide, using the HTT data as an example, we can see that in this bar plot, only the sample number 2 has repeat expansions beyond the pathogenic threshold. In the next few slides, I'm going to go through the sequencing data with repeat expansions. For sequencing reads on the SCA1 related region, we see 3 samples with repeat expansion above pathogenic threshold. Samples number 5 and 6 are confirmed cases in clinical diagnosis. Sample number 3 was an undiagnosed sample. For sequencing read in the SCA2 related region, we see 1 of the sample, sample number 7, has repeat expansion above the pathogenic threshold. This agrees with the clinical diagnosis. And we also see that for the repeat expansion in this sample, the sequencing data has 3 CAA repeat sequence interruptions. For sequencing data on the SCA3 target region, we see one of the sample has repeat expansion above pathogenic threshold, but the other sample does not show any repeat expansion in the sequencing data. This confirms that the sample that has conflicting diagnosis data is not a SCA3 sample. For the Friedreich's ataxia sample, we see repeat expansion with about 600 copies of GAAs in the sequencing data. For the second undiagnosed samples, sample number 4, we see in the sequencing data that there is repeat expansion just above the pathogenic threshold for the SCA17 related region. For the last 2 undiagnosed samples, we see FMR1 repeat expansion in the pre-mutation range. Sample number 12 has about 95 copies of CGGs with 1 HGG sequence interruption. Sample number 13 has about 75 copies of CGGs. Overall, our sequencing data agrees with the clinical diagnosis result very well. For the undiagnosed samples, for sample number 3, we see repeat expansions in the SCA1 region. For sample number 4, we see repeat expansions in the SCA17 region. And for the last 2 undiagnosed samples, we see FMR1 premutation repeat expansion in the sequencing data. Other than the pathogenic repeat expansions, we see repeat expansions with normal sequences in SCA31 region and SCA37 regions in 3 of the samples. In conclusion, we have demonstrated using the No-Amp targeted sequencing method with repeat expansion panel to successfully sequence 17 different disease-related repeat expansion loci in 13 human cerebellum samples. Repeat expansions observed in the sequencing data agree with confirmed medical diagnosis and reveal mutant loci in samples with unconfirmed diagnosis. The method is not only a useful tool for studying repeat expansion genetic disorders, it could potentially be used as a molecular testing method in the future. Finally, I would like to point out that the benefits of capturing and sequencing specific genomic regions without amplification includes no PCR amplification bias and preserves epigenetic modifications on DNA templates. This is the end of my presentation. Thank you very much.